Okay, my name is Brad, and I'm going to solve a statically indeterminate problem here. So as you can see, we have our setup here. We have a solid cylinder here. We'll say it's made of brass, I guess. We'll say it has a flexibility of F sub B. We also, above the cylinder of brass, we have a cylinder of copper here, and we'll say it has a flexibility of F sub C. And then surrounding the cylinder of copper, we have a pipe right here, and it is made of steel, and it has a flexibility of F sub S. And our goal here is to find the reaction forces here of R sub C, R sub S, and R sub B. And the whole system here is also constrained by the ceiling and the floor here, I guess you could say, which they don't move. Okay, so our first step here is to use our statics, or find our equations of statics, I guess. So we know that the sum of the forces in the y direction has to equal 0. So we have RC plus RS here have to equal the forces opposing them, which are F naught and RB. I forgot to mention there's a force F naught acting right at the top of the solid cylinder of the brass here, so you can see there. Okay, so now that we have our equation, our static equation here, I'll call it equation 1, we want to find our force displacement relations. And so that's pretty much our delta S, delta C, and delta B. So if we draw our box here for delta B, we can see that delta B must equal the flexibility of B times the reaction force at B. And the same pretty much goes for delta S and delta C. Alright, so those are our force displacement equations. Oopsies. Alright, there we go. Okay, so now our next step is to find our equations of compatibility. So first off, we can see, kind of from looking at the picture here, that delta S and delta C are going to have to be the same, because the length of the steel pipe and the length of the copper cylinder are going to have to be the same, so their displacements will have to be the same as well. Alright, so you know what, we're going to go over here. Alright, so delta C is going to have to equal delta S. And we can also see that the displacement of the steel pipe and the displacement of the brass cylinder are going to have to sum to 0 since they are stuck between the ceiling and the floor here. So we're going to have delta B plus delta S equals 0. So we'll call that 3A and 3B. So now at this point it's pretty much a matter of algebra. So I guess what we'll start with is we'll take equation 3A here and we'll write it out. So delta C equals delta S, and what we want to do is substitute in our force displacement equations. So we found that delta C equals FCRC, so we'll substitute that in first. FCRC, and then we found that delta S equals FSRS. And then for 3B here, we have delta B plus delta S equals 0. I'll move the delta S to the other side here. Oops. So we'll have delta B equals negative delta S. And then, again, we'll substitute the force displacement equations that we found. So we have delta B equals F B R B, and that equals negative delta S, which we found to be FSRS. So now, for this equation here and this equation here, I'm going to solve for RS for both of them. So here we can see that if we divide the FS to the other side, we'll have RS equals FC RC. You know what, actually, okay, for this equation, made a mistake here. We're going to solve for RC actually. So we have RC, and if we just divide the FC over to the other side, we'll have RC equals FSRS over FC. And similarly down here, if we solve for RB, we'll have RB. If we just divide the FB to the other side, we can see we'll have negative FS RS divided by the flexibility of B here. So now, if we, our next step we want to do is to substitute this RC and this RB into the statics equation, our first equation up there. So we'll just rewrite that equation here quick. RC plus RS equals F naught plus RB. Okay. So, I guess first I'm going to move FB to the left side of the equation. Okay, so now we want to substitute RC in here, so we see that RC equals FSRS times FC. So I'll just plug that in here. FSRS, FC, and we have the plus RS, and again the same thing for RB here. So we're going to have minus and negative, so it's going to end up being adding minus and negative. So we'll have FSRS over FB, and everything here is equal to F naught. So now we're going to factor out an RS. So here if we take out the RS, we're left with FS over FC. If we take out the RS there, we're just left with 1. And then here we're left with FS over FB. And that's equal to F naught. So, to solve for RS, we just divide this quantity over to the other side. F naught, and divided by, okay, so we have 1 plus FS over FC, FS over FB. So there's one of the equations we're looking for. So yeah, we're looking for RB, RC, and RS, if I didn't mention that before. So we have RS now. And so now what we can do to find RC and RB is just substitute this value into these two equations. So I'll start with RC. Write what we know. Let's rewrite this equation. RC equals flexibility of S times the reaction at S divided by FC. So now we're just going to substitute this RS here with the quantity we found down there. So RC is going to equal FS over FC. Okay, so then we just want to plug the RS in here. So, alright, I guess we'll have looks pretty messy, but that's our equation for RC. All of these values are known, all the flexibilities are known, and F naught is known as well. So that's solved. So now our last thing we need is RB, and that's pretty much the same thing here. Just rewrite the equation. RB we know to be negative Fs times Rs over flexibility of B. So now again we're just going to substitute Rs in for Rs here. The reaction at B is going to equal negative Fs over Fb. And then again we're going to substitute this whole quantity in here. We have F naught over 1 plus Fs over Fc plus Fs over Fb. Alright, and this could probably be simplified a little more, but at this point all you would really do is plug in the known values here, and you would have your reaction forces. And so there you go. That's a statically indeterminate problem solved.